of this signaling yourself. So, if you were to get an Arduino and hook something up over I2C, it makes it look nice and simple with all the start bits, stop bits, NACs, ACs, all that stuff, because it hides it from you. And it's actually a blessing that it does because it's annoying. But here on the Gecko, you have to generate all of these bits on your own. There are certain registers that you're going to use, but you have to create all of those bits. So again, the general structure is the same. Transmit buffer, it gets shifted out. Receive buffer, clock generator. It's generally the same structure as you've seen with the other peripherals. The only real thing that you have to configure is the clock frequency, and the clock frequency is determined by the period of how long the clock is high and the period of how long the clock is low. So depending on how those two are arranged, that gives you the overall clock frequency. So there's a parameter that you set that gives their relationship, and then that gives you the high-low. We're not going to have an asymmetric clock. The clock should be 50% high, 50% low, because we're not going to be going very fast. You're going to be in standard mode where everything is kept below 100 kilohertz. So what you see is, depending on the bus frequency and the ratio that you pick for your clock, you get sort of various speeds. So you can go up to almost a megahertz if you choose. Travis?
So on the previous slide,
yeah.
So it is T high plus T low and then T high over T low?
No. This is a subscript. So this is how you calculate the clock frequency, and if you assume that they're the same, that there's a 50%, then T high and T low is calculated by this. So like this is the rate, this is a ratio factor of high to low, and then that gives you either high or low.
So in our case, N high low would be
1 or 50, or you have to look at, let's see how you do the calculation. Yes, it's just 1. Like there's no real ratio there. General theory of operation is you throw the data in the transmit buffer, and once you issue a start bit, you have to manually issue a start bit, it starts to go, it starts to run. The master has to generate all of these signals, but there is a command register that you use to generate them. So like with the timer, you can start the timer, you can stop the timer. Here you have a similar command register that generates NACs, ACs, starts, and stops. All of those bits have general sort of interactions and priorities. So if you have an ACT pending but also a stop bit pending, the stop bit is going to have higher priority and just sort of shut the bus down. So you can queue up interactions if you wish, but if you do a higher priority one, it will shut everything down. This is probably the most important slide. This is probably also the most complicated slide. This is the state machine that governs the I2C bus. So documents produce a set of rules about how devices should communicate. This is the resulting state machine from the master perspective. So the idea is that if you are the master device and you are a transmitter, you have to follow this set of series of events. And if you are a receiver, you've got to follow these. It's a big state machine, but you can ignore already a third of it. So generally, transmit, here's receive. Here's what happens if you lose arbitration. You're going to be the only one talking to us, so you don't care about this. So immediately, you can already just kind of get rid of half of it. And the way that you want to read this is that this is the state of the bus, and these lightly colored boxes are things that the master does. So it waits for the bus to become idle, and then the master transmits a start bit. So S there means start. And everywhere you see one of these bubbles, that is the value of the state register inside of the I2C unit. So what they're doing is they're taking all these status bits and all of these state bits and they're encoding them into a number. So if you look at that register inside your IDE, you'll see the number. It says start bit. If you happen to see a different number, then that means you're in a different state. But the idea is that once you transmit a start bit, you then need to transmit an 8-bit packet that has the address with a write bit. This is if you wanted to write data. You will then wait for an acknowledgement. So these lines here generally sort of mean like waits or events that you have to respond to. So you send a start, you send an address packet with a write, you wait for the slave to acknowledge. So the white boxes, the empty boxes, are things that the slave device will do. So once you receive that acknowledge, your device moves into a different state and you can send data. Once you send the data, you can then, the slave device will acknowledge it, and you can keep going through this loop. You can keep sending data, acknowledge, data, acknowledge. And you can keep going on and on through that loop until you either do one of two things. You either stop, which is P, so P means stop the bus, or SR, which is a repeated start. You send another start command, which means you are not releasing the bus, but you are starting a new transaction on the bus without giving it up. Okay. Questions on this? Because if you do not understand this chart, you will not get through the lab. Because what your lab is going to be is implementing each of these state machines. So you can imagine one machine here, transmit, there's one machine here or one process here for receiver. The important part of this is that, once you've transmitted some data, two things can happen. You can either get an acknowledgement or you can get a NAC. You can get a NAC acknowledgement. You can get a not acknowledgement. And based upon either one of those, you have different things that you can do. Basically, if at any point you receive a not acknowledgement, your transmission has failed. So if I send out an address and no one hears it, I get a NAC. Or you never receive anything and you sit there in that state forever. You get a NAC. If you send data and the device never receives it, you will get a NAC as well. So if at any point you get a NAC, that means that something failed. One of your transmissions failed. And you need to just basically stop the bus and then get out. If you don't stop the bus, that means you never release the bus, and when you come back to that code, you'll be in the wrong state. So you don't want to write your code and just go, let me transmit this. Ah, crap, I got nacked. And then you just type return. Like, you can't just bump out of your code. You need to complete this machine and either do a repeated start or a stop. Like, you have to follow this machine through. Bill. Because you could try again. Like, let's say, you can. Like, you've submitted like a not right and you got nacked, and it probably doesn't want you to come back here to data. Like, that doesn't really make much sense, but the idea is that you've got to come back here. Like, this line shouldn't necessarily flow back to here. Although this line can go back and you can send more data. This line can go back and you'd be like, we're going to try it again. But it doesn't make much sense to try to send data again if you lost over here. So like, if I open communications with Travis and I throw some data at him and he doesn't get it, I might try it again. But it doesn't make any sense to Travis. Here's it. I'm just going to hit him in the head. I'm just going to throw it at him. The same thing with the receiver. They're generally the same thing, except on the receiver side, you are doing the address plus a read bit. Hey, I heard you, and then the slave device sends the data, and you can either acknowledge, meaning give me more data, or you can not acknowledge, which means I'm done, I've had all the data I want. You can either stop and release the bus, or you can start again and try a new transaction. And you'll see here that this goes to 57, which is that state back there. So it's a complicated diagram, but you can automatically ignore half of it. And you're going to need to implement every box there is going to be a piece of code that you write. Like you're going to need to write one line of code that sends a start bit. You're going to need to write one line of code that sends the address plus the read or write bit. You're going to need to write one line of code that waits for that acknowledge or not acknowledge. You're going to need to write one line of code that transmits your data. So your lab is not a tremendous amount of code. It's only these two machines, but you have to follow these machines exactly, because that means you're conforming to the bus protocol. So again, the top part is just general operation. This should never happen down here, because there's no one else in the bus. You should never lose arbitration. And again, the color coding means lighter gray is stuff the master device does. These bubbles are the exact value of the state register. So if you pull up the state register in the registers tab in your IDE, you will see the number 57. And if you see the number 57, that means you have transmitted a start bit. You now need to transmit an address bit with a write, and so on and so on. Those are your different sort of states that you need to do. The way that this sort of looks is to do all of your actions except send data, to send all your start bits, your stop bits, your NACs, your ACs, there is a command register. And in the command register, you can say what actions you want to take place. So if you wanted to send a stop bit, you would put a 1 right here. And so you would put a 1 in the bit 1 position, and that will, boom, when it's time, send a stop bit. So you can imagine that you're going to be doing a couple of these in your code. So everywhere in that box that it says send a start, you want to put a 1 here. And every time that you need to acknowledge, you want to put a 1 here. So you could come up with a little function that's called send start, send stop, send NAC, send act, if you wish, and those functions would just be one line of code. Wouldn't be that much to do. At the same time, there are two major registers that tell you what's going on. The state register gives you the general state of the I2C bus. It tells you what's going on. And those state bits, when you're looking on that chart and it says state is 97, it's talking about all of these bits. It's talking about all those bits there. There is a lot in here, whether the bus is busy or not, whether you are the master or not, whether you are actually transmitting or not, whether or not you have been nacked during this transaction, whether the bus is being held. If you're doing stuff, you are holding the bus. And then there are 3 bits here that, in more detail, encode the state of the bus. So these 3 bits tell you exactly what's going on. So if you read this and it's 0, then the bus is idle. If you read this and it's 2, that means that a start bit has either been transmitted or received. And you're never going to be a slave device, so this will always be from the transmission perspective. So if you see the value 2 in that field, then you know you have successfully just sent a start bit. And if you're looking at these slides and the other slides are probably not there. These are new slides. So even more, you have the graphical state machine. They have taken that state machine and they've also turned it into a table. So if you find yourself in this state 57, here's what may have happened, here's how you'll know, and here are the things you can do. So if you've just sent a start bit, you can send an address with a read packet. You can send a stop bit. You can send a start bit, then a stop bit. Like, it tells you a list of things that you can possibly do once you're in that state. This is way more information than you need. You really only need to follow that graphical diagram. And this is only for the master receiver chart. So this is that second sort of state machine turned into a table. And again, the interactions have priority order, so if at any time you say stop, a stop will get sent before an abort will be sent before a NAC or an act. So they have priority on them, but you'll only really ever be doing one command at a time. Okay, this can be really confusing, but we're going to simplify it in one of two ways. One is, there are two ways to simplify it, we're going to do one. First way to simplify is be the only master on there and don't do a multi-master system. So you don't have to, in a multi-master system, that means that masters can talk to other masters, which means that some devices become a slave device on demand, which means that that state machine gets even more complicated. So you don't need that. So if you only have one master, then you never lose arbitration. So that whole bottom half of the chart, gone. The second thing that you can do is something called automatic controls. Now I put this in here because it's a feature that should remove automatically sending those ACK and NAC and start and stop bits. So it'll automatically do it for you. It's supposed to simplify things. However, you have to make sure that your device conforms to those automatic controls. We're not going to use the automatic controls because the accelerometer is not necessarily going to conform to that specification. So the same thing when we were talking to the accelerometer over SPI, there was the automatic chip select line. And I said don't use it because you'd like to have explicit control over that line. Same argument applies here. Like, you should probably send your own start and stop bits instead of trusting that the hardware is going to do it for you at the right time. Here's your overall configuration that you need to do to get this up and running. The configuration is a lot easier. When you pick your pins, you have to put them in a mode called GPI mode wired and. So they have to be wired and, which means, and you have to make them set output high, which means they're going to naturally float high, and then they can be pulled down low. As before, you've got a location register. The location register is going to pick, you've got a route register, and inside of the route register, you can turn on and off your pins, and you can set which location you are going to use for your pins. We're going to use location 0. You got to set up your clock divider. You got to calculate your clock divider. You got to set it up, and then you've got to just enable the I2C module in the control register. So it's really, really 4 easy things to do, not that hard. Once you've configured it, though, the first thing you should do is just send an abort command, because that just stops everything on the bus and resets it to a known state. So you're going to have a function called setup, and you want to do this, 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 and then once you're done, send an abort command to clear the bus. All right, overall I2C on the get-go. A lot of configuration that you have to do. So you've got to send your own start, stop, ACK, NAC, data bits. You've got to send them all, but there are a lot of registers that tell you the current state of the bus and the status of the bus. You can simplify things with automatic controls, but we're not going to use automatic controls. You're going to manually do these. It's not as complicated as it looks because you're going to be the only master. So the core thing in this lab and in this section is understanding this chart. And if you can't go through this chart, I think you're going to have a hard time. Ben?
Do you have these slides online? I think you...
Yeah, I don't have this one up yet. Yeah, the old ones are still up. I made these up this week. Or I added to these. Like, this is a new slide. I think this is a new slide. So there's not much different. There's a couple new slides. You'll have them up when I'm done. All right. Let's move over to the lab. I emailed you out the lab. I emailed you at the lab, and I did it yesterday morning because some folks had asked to have it early, and just in fairness, I sent it all out to you. It wasn't fully complete, but at least you knew what we're doing and what we're working on. Lab 4 is back to this guy, but you are going to use the I2C interface. So instead of connecting chip select, MISO, clock data, all that, you're only going to actually connect up 2 lines. You're going to connect the clock line, and you're going to connect the data line. You'll always need power, and you'll always need ground. Here's the difference, though, is that you only need to make these 4 connections. And one benefit of this device is that they've already built in the pull-up resistors that are needed for the I2C interface. So you don't need to go to the back and fish out some resistors and use a breadboard. You can directly tie your pins. You can directly tie your pins to your processor. They've thought about this with this board. They've done some things to help you. The chip select line is naturally tied to high, which means that if you're doing I2C, it's naturally just sort of, if you're doing SPI, it's naturally sort of inactive, and then when you pull it low, it becomes 0, you can talk to it. That also means that by default, this device is in I2C mode. So whenever chip select is high, it's in I2C mode. So by default, we're in I2C mode, and they have already given you the pull-up resistors needed for the clock and data lines. So you don't need to add those. That's actually really convenient. It's less stuff. The final thing is that there is the way that the device is configured, depending on how this SDO line, which is serial data out, which we don't use, depending on how that's configured, you can change the address of the accelerometer. You can change the lower bit of the address. And they have already tied it to high. They've already tied it to high, so you know what the address is. And I'll leave this slide in the documentation for you to figure out what the actual address is. What you're going to do is you're going to connect here to 3 volts, you're going to connect to ground, and then you're going to connect to I2C number 1, location 0. Now I have a story about location 0. So I tried to do this lab last year. Never did it work. Never did it work. The chip works on Arduino, wouldn't talk on the Gecko. Gecko never works. And once you see how much code you have to write, you'll see how annoying it is to talk to the Gecko. Try this lab again this year. I spent 2 days on it. Nothing worked, nothing worked. I would get data, it's bad data. I changed out chips, I moved to Arduino, I tried different stuff. The one thing I never changed was what pins I was communicating on. So if you all did that, I would say, oh my God, how do you not change your pins? Just try it out and see what's different. I wasted probably like 20 to 30 hours and like over a year ago couldn't do this because I never said, let me change what pins I'm on. Because like, why should it matter? Why does it matter if you're on location 0 versus location 1? It turns out it does. I have no idea why. I have no explanation for why the exact code works on these pins, not on these pins. I have no idea. Maybe it's the way the board's made. No clue. You need to use location 0, otherwise if you use location 1, it'll never work. And also take that lesson that if you think the code's right and it's sort of working, just try a different set of pins. And why things work on one set of pins and not the other, I have no idea why, because sometimes it does matter. And this is one of those examples. Probably some silly electrical engineering reason why there's a difference. So, location 0, just use it. So, if you took a look at the lab, there are a lot of files with the lab. You have the same main file as you did from lab 3. So it's going to do a self-test, it's going to grab 3 accelerations, it's going to calculate a vector. That helper.h file got turned into a class. Because if you just have a header file and you include it in 2 different classes and the classes reference each other, then it's a circular inclusion for the header and it can't be resolved. And it's a pain in the ass. So the way that you solve that is that you make the helper a class. So all the helper functions that you had now become static methods in classes. So where you had read bit, it's now helper, : read bit, there's your function. So they're all given to you, they're all there, you can be happy with them, but they're all as part of a class now. I have given you my implementation of the accelerometer code. You do not need to write any code for the accelerometer. You don't need to configure the accelerometer. I take care of all that. So if you were not successful on lab 3 in dealing with the accelerometer, that doesn't matter because you are not configuring the accelerometer at all. The only thing that you are completing is this file called custom I2C. And so it's sort of a wrapper for the I2C data structure that we control. And there are two major functions in there called read and write that you have to implement. I have also given you several helper functions inside of that class. Because you're going to have enough trouble going through the state machine itself, I've given you sort of all the hooks to read the state of the bus. So one of them is a function that returns those little state bits inside of the state register. Those bits get cast as an enumeration. What that means is you can call a function called get I2C state, and you will get one of these words back. So you can say so if you're going to wait for the bus to become idle, you can say get this state here while the state is not idle. So what an enumeration does is it basically replaces this word with a number. So this is 0, 1, 2, 3, 4, 5, 6, 7. And if you look at the way that state register is laid out, a 0 response means idle. A 1 response means wait. A 2 response means start. Because the enumeration is in the exact same order as those bits, and those bits are in contiguous order, you can do this. So it's a neat little hack to sort of make the code more readable. So what I do is I take those bits, those 3 bits, I shift them down, I AND it with 7 to kill everything else. I cast it as the enumeration, and I return it. So you get that function. There are also other functions in there that will return if something is an act, or if data is ready. And those are just reading bits and returning them. Here's what you need to do. You need to implement a function called read register and a function called write register. Read register is used by the accelerometer to read an internal register. Read register is used by the accelerometer class to read a particular register on that device. So it passes in an address, and data, or returns data, whether or not it's needed. There, inside of the accelerometer data sheet, there are 2 timing diagrams, if you wish to call them that say how to do writes and how to do reads. They have them both for single bit and single byte and multi-byte operation. We're only going to do the single byte reads and writes. It's simpler. Your code is much easier, and honestly, given the speed that we work with, you don't have to do it as much. What this says here is that for a single write, here is what the master has to do. Here is what the slave has to do. And you should see how this really, really closely corresponds to the state machine that the gecko has. You're implementing the same states and the same operations. You're just maybe doing it in a slightly different order because that's the way he wants to receive data. So the way that you want to interpret this is that if you're going to do a write, if you want to write to a register on the accelerometer, the master has to send a start bit along with the accelerometer's address and a write bit. If he gets it, he will then acknowledge. Once the transaction's been set up, the master will then send the register address that he wants to write to. For some reason, the documentation they use sub to mean like sub-address, which is pretty dumb. I don't know. What the word sub in here is talking about the internal register address that you want to either read to, you either want to write to or read from. So it'll acknowledge, you give it the register that you want to write to, it'll acknowledge, you give it the data that you want put in the register, it'll acknowledge, and then you'll stop. So it's very similar to the SPI operations of like, here's my address, here's the data, but you've got some acknowledgments in there. It's very similar, but instead of turning the chip select line up and down, you're doing start and stop. It's the same general idea. Questions on this? You need to understand this. So if you're going to write to register A and if you're going to write A to register C, you would say start, here's your address plus W, acknowledge it, I got to talk to C, boom. I got to put A in there, boom, and you're done. And that's what the protocol is. Same thing with a read. Now the funny thing about a read is that you basically write the address to the device and then you start a new transaction that's a read. So you do one transaction that says, hey, here's some data I'm giving to you. And then once you write that data, you then have to read it back. So you can start, you do a write transaction to the device, and you give it the address that you want to eventually read from. They will acknowledge, and then you start a new transaction. The SR means repeated start. So you don't say stop. Don't say stop here. You say start. It'll do a repeated start, and then you'll read from it, and it'll give you the data back. And once you get the data back from it, you can knack the transaction and boom, say you're done. If you acknowledged it, it may keep giving you more data if you have the multi-byte operation on. So the way that this works is if you wanted to read from register CF, you would do a write transaction, you would write CF into the device, you would do a repeated start, you would do a read transaction, you would get the data back from that. So the big difference here is that you're going to write the address that you want to later read, and that you have a repeated start. A couple things you got to figure out. What's the address of the I2C? I don't know. Look it up. You've got it in the data sheet. You've got it directly in the SparkFun schematic. You can figure it out. You need to understand that I2C protocol diagram. If you don't understand that diagram, and if you don't understand how the accelerometer wants to receive the data, you're never going to get anywhere. There's no way that you're going to be able to fumble around and write code that's going to work. You have to be very directed about it. You have to be very intentional about it. Like, it's not going to magically work. There's too many conditions that have to happen in an exact order for you to get close. My advice would be to take the read register function, the write register function, and every action that you got to do, put a comment. And everything you got to wait for, put a comment. If it's something you got to do, hey, that's a command, or that's a write to the transmit register. If you've got to wait for something, you're probably going to sit there and poll on that get status function until you get to the right state. So if you make line of code, line of code, line of code, and then walk through that state machine and it lines up, then it's going to be right if you put the right operations in the code. One fail-safe is to always check for naps. Check for not acknowledgments because you may get napped. You may be sitting there in your code and it's not going anywhere, not going anywhere, not going anywhere, but then realize that you got napped, which means you did something wrong earlier. You're either talking to the wrong person, you're using the wrong pins, like something's going wrong. So always check for naps to be able to bump out of your code to make sure that you did the transactions correct. What you've got here is 3 major tasks. This is the same as with the accelerometer. Task 1 is set up the accelerometer. Set up the I2C. Again, it's just 5 little steps. Configuring the pins, configuring the clock, and there you go. 40% is passing the self-test. So to pass the self-test, you need to be able to implement read register. If you can't implement read register, you're not going to pass the self-test. If you can implement write register, then you will pass the other acceleration tasks. So where they get some data, you will pass those as well. So it's only really 2 functions to implement, and maybe a couple more that determine whether something is an act or act. It's not that much code, but it's code that really has to be written in the same order. So really, before you just dive in and write code, like write down on a piece of paper what's going to happen and what the plan is, because just coding this up is going to get you nowhere. I have made this due next Tuesday night, so like right before your exam. And so I know people are going to wait until like the last minute to do it. The difference I'm going to be on this one is I'm going to be honest to God stickler on the due date. Like it's 11:59. Like give it to me by 11:59. Like I have to have it by then because the next day's the exam. The next day I take the keys away. Like I gotta have it. Because you don't want me to just be like, well, I don't have it, it's a 0, because like this is going to be like 50% of your grade. Like every lab is a big chunk. Just get it to me on time. You've got 11 days to do it. Let me show you the code that you've got. So I have all the code posted on GitHub. We've got lab 4. You got a bunch of files. You only need to care about one of them. But your main file here, it's exactly the same as before. I've given you everything you need to know. You can ignore that comment about it dealing with the spy bus, because that's just old code. I'll change that. But everything's exactly the same. Your helper functions are now turned into a helper class. I have also given you all of these functions. You'll see that they're all static methods. So instead of calling the function directly, you'll say helper : name a function that you wish. That's how you access a static method in a C class. And you can see an example of that in the code. The accelerometer, I have given you my code. You have my code here that does everything. So this is my implementation of setup. This is my implementation of the initialize. This is my implementation of everything else. What you'll notice is that in the constructor, it grabs a pointer to the I2C interface. Technically, it grabs a pointer to the custom I2C interface that you will use, and it grabs it as a singleton, which is statically allocated, so you're not going to be talking to multiple devices. The only thing that I changed in code from my SPY version to this version is I changed how write register was implemented. So previously, I would change the chip select line. I would then do SPY transfer. I deleted all that and just now call write register. So where your old class would try to write to an internal register and write a value, here you've got to write to its I2C address, its address, and then its value. So you've got to figure out what the I2C address is. And I'm looking at the code now, and I may have left the I2C address hidden in the code. That's fine if you can find it. Same thing with the read register. The write register works exactly as you think. It takes an address, and it takes a value, and it writes it. It returns true or false, whether or not it's successful. The read register is a little different. Normally with a read function, you return the data that is read. I wanted to return both the data that was read and a true or false about whether it was successful. So you've got two options there in C++. You can either return a structure that contains both variables, or I sort of, not cheated, but it returns true or false, and you pass in a pointer to a byte. This is the byte that will contain the result. So it reads a register, and the result is then placed in that byte, and that byte is what actually gets returned out of here. So you really don't need to concern yourself with these two functions because they're implemented for you already, but you can kind of see what's going on. Okay. This is the thing that you care about. This is your custom I2C class. Here are the enumerations of the state. You've got, this is how you get a handle to everything. You've got your write register function, your read register function. Those are what you have to implement. This is, again, implemented as a singleton, so the constructor is private. And set up clocks, set up GPIO, set up I2C. You need to implement those, same as before. Turn on the high frequency clock, turn on the GPIO clock, turn on your GPIO. And then I have given you a couple functions here that will be useful. Is the data valid? Is the bus busy? Is it NACT? And you can see their implementations here. So you've got to do set up clocks. You've got to do set up GPIO, I2C. I even gave you this thing at the last, which does the abort. Make sure that's last. You need to implement this function, and then I give you functions that tell you whether you've been nacked or whether the bus is busy. So you can use these functions to your benefit. So again, the helper function, the helper header is now a class, and so you call things statically that way. So here's all your code. Everything that says to do, you have to implement. So you've got five functions to implement. About beyond advice on that, you really need to get. Let me show you what the lab sheet looks like. Again, this is the same thing that was contained in the slides. I just put it here. You need to have the lecture, you need to have the slides, you need the Spark Venn diagram, you need the source code. Here's the grading. I have the same bonuses from the Spy Lab. You don't get to repeat them for double credit because it's the exact same code. But if you have not availed yourself of those bonus opportunities, I will leave those up for you to do again. And if you do anything more complicated, like using timers or interrupts or double tap, talk to me. We'll talk about doing it. But if you want some extra points in the lab, there you go. So if you've done them before, you don't get to double dip, but they're there for you again. Give me all your source code when you submit it, all header files, all CPP files, everything. Give me all your source code. I just dump it in the folder and I copy and paste it over, and that's how I grade. I also run everything through MOS just to see how everyone is. Yeah. Final. Travis, yeah.
So the select line should be right.
You don't have the chip select line on this board. You do not have to do anything with
The
it.
SCL.
The SCL is the I2C clock line.
Yes.
Yes.
That needs to be the grounded output, correct?
No, so initially they all need to be set up in GPIO, and it's wired out, and they need to be all high as a default. So use the GPIO pin mode set function to say this pin, GPIO ANDed or ANDed, wired and then make them high. Is the way to do it.
For both?
For both pins. They're both, they need to be high naturally. They just need to be, the bus needs to be high. Both the data and the clock lines. Okay. I would get on this now, today. I'm here today. I'm here Wednesday. Sleeping on people's couches, so I have a little more availability because I don't own a house. But I'm building a greenhouse, so maybe I'll live there. That's why I'm dressed so shabbily. But please make sure you dive into this. This is your last big milestone. The next thing you got is the exam. You only have 2 big things left in 11 days. And I don't think the exam will be that challenging if you pay attention to the lectures and if you've gone through the lab. That's sort of my advice on those.